Good morning, everyone. So today we're gonna start about recent advances in restorative materials. The contents will be introduction, recent advances in amalgam, recent advances in glass ionomer cements, and this we are following different types of modifications and advances. Then we have recent advances in composite and then ceramics, and we have smart materials and summary conclusion. Introduction. Different types of restorative materials and luting cements are currently used in daily dental practice. The most common are amalgam, composite resins, glass ionomer cements, ceramics, etc. Each material has several advantages and several disadvantages. To overcome the drawbacks of various materials, there has been a continuous research for the advent of newer and better restorative materials. Now, first is recent advances in amalgam. First is bonded amalgam restoration. Despite all the advantages, amalgam has its own limitation as a restorative material. It lacks adhesion to the tooth structure and thereby requires considerable removal of more intact tooth structure to provide long-term retention. Accordingly, amalgam weakens remaining tooth structure rather than strengthening it. This is the main reason for cuspal fracture and long-standing silver amalgam restorations. Other limitations of amalgam restoration are increased micro leakage under amalgam restorations, decreased tensile strength under complex restorations, and corrosion. To combat the above mentioned limitations, adhesive system designed to bond amalgam to enamel and dentine have been introduced in an effort to compensate for the disadvantages, particularly micro leakage and need for additional retentive devices. Advantages. The advantages of adhesive amalgam restoration over non-adhesive treatment are: it is a treatment option for extensively caries posterior teeth with lower cost than either cast metal restoration or metal ceramic crowns. It allows the use of amalgam in teeth with low gingival occlusal height, which is not possible in conventional amalgam. Amalgam with pins, inlays, onlays, complete cast crown restorations. It permits more conservative cavity preparations as it does not require additional retention in the form of groove, pins, etc. It can eliminate use of retention pins and inherent risk involved with it is such as periodontal perforation, pulp exposure, stress patterns, cracking, crazing, etc. It reduces marginal leakage to minimal. It reinforces the tooth structure weakened by caries and cavity preparation, which is not with pin amalgam. It reduces incident of post-operative sensitivity commonly observed with amalgam restorations. It reduces incidence of marginal fracture and recurrent caries. It allows biological sealing of PD complex by formation of hybrid layer. It can be done in single sitting. It allows for amalgam repairs. Amalgam bonding agents. Some amalgam bonding agents which are able to bond amalgam to tooth structure are, so these are the various examples of amalgam bonding agents: amalgam bond plus, all bond 2, and AU bond liner F, and a Panavia X. The chemical composition of amalgam bond plus. So it has one activator or conditioner, that is 10% citric acid, 3% ferric chloride. Then we have adhesive, that is HEMA, hydroxyethyl methacrylate. We have catalyst, that is TBB, tri-N-butyl boron oxide. And we have base. Base is formatted, that is for methacryl oxyethyl trimethylatate anhydride. In the mechanism of bonding. First, the dentine and the enamel are treated with acid conditioner, that is 10% citric acid, 3% ferric chloride for 10 seconds. So first we condition the dentine and amalgam, citric acid and ferric chloride. Then this causes the removal of smear layer and partial demineralization of collagen, with removal of only apatite mineral and preserving the integrity of dentinal protein molecules. These open pores are now penetrable by 4-meta or MMA-TBB monomer. Now, monomer penetration can be improved by treating the surface with the application of HEMA. So, what we have done is, first we have treated the dentin and amalgam with acid conditioner so that it removes the smear layer and partial demineralization happens. Then, now we have got open pores because of the removal of smear layer. So these can be penetrated by 4-meta. Now monomer penetration can be improved by also treating the surface with the application of HEMA. Once polymerized, the resin formed not only entangles and envelopes collagen, but also encapsulates hydroxyapatite crystals, creating the acid-resistant insoluble transitional zone hybrid layer. The width of hybrid layer is 5 microns and is sandwiched between cured resin and dentine. So this is first we prepare the smear layer, then conditioning that of the collagen network, then priming of hybrid layer, and adhesive is copolymerization with composite. So this is how the mechanism of amalgam bonding agent works. Technique. Due to bonding system available, minimal retention form is required during cavity preparation. However, cavity preparation still requires adequate resistance form. Fragile cusp and walls should be reduced. After proper isolating and anesthesia given, all caries tooth structure is removed. Surface is etched with 10% phosphoric acid gel, then washed for 15 seconds and dried with air jet. After drying, conditioned enamel has dull white appearance, that is frost white appearance that we say. 3 coats of primer A and primer B are applied till shiny aspect caused by hydrophilic resin incorporated in primers is obtained. The dentin enamel bonding agent is applied with brush and freshly triturated amalgam is condensed into the cavity before the auto-curing bonding agent is polymerized. So, first, clinical procedure, upper second premolar with fracture disto-occlusal amalgam restoration. We have placed rubber dam with interproximal wedging, showing the fractured amalgam has been removed along with caries. Next, after etching and priming, a thin layer of bonding resin is applied to the cavity using a disposable brush. Next, wax-coated stainless steel matrix band has been applied and wedged. Then amalgam placed and heavily burnished. After that, a gel is placed occlusally and interproximally to allow complete anaerobic setting of adhesive resin. Initial carving and removal of matrix. After removal of rubber dam, occlusal adjustment and final carving and polishing is done. Now, limitations of bonded amalgam. Time consuming and technique sensitive due to bonding agents used. Requires practitioner to adapt a new technique and increases the cost of amalgam restoration. So this is the article. In this, the effect of amalgam bonding on the stiffness of teeth weakened by cavity preparation. So this is the article on this. Cavity preparation reduced the stiffness and weakened the tooth. Restoring the prepared tooth with unbonded amalgam did not restore the lost tooth stiffness. It was concluded that bonding amalgam to the tooth structure could partly restore the strength and rigidity lost by the cavity preparation. This might lead to a reduction in cuspal flexure and the incidence of the tooth fracture due to fatigue. Bonded amalgam sealants and adhesive resin sealants, 5-year clinical results. So this is also one of the articles. Bonded amalgams were used as pit and fissure sealants without mechanical preparation. They were compared with a resin-based pit and fissure sealant for retention over a 5-year period. Clinical examination has 6 months, 1 year, 2 years, and 5 years revealed no difference between the two techniques. They can be used to seal pits and fissures surrounding very conservative preparation in the preventive amalgam restoration. Conventional amalgam retentive features and 90-degree cavus surface margin may not be necessary when bonding is used with amalgam. Now, effects of surface roughness on amalgam repair using adhesive systems. Result: the use of adhesives have been suggested for repairing amalgam restorations. associated with the roughening of an old amalgam surface. The application of an adhesive system could improve bonding between old and new amalgam through mechanical interlocking between the adhesive system and freshly condensed amalgam. The irregular surfaces are micromechanical retentions for bonding of primer due to old amalgam and can be created with a carbide burr, diamond burr, or aluminum oxide particle abrasion. Now, development of silver-based mercury-free restorative alloys. Although amalgam remains the most inexpensive, reliable, and popular restorative material for posterior teeth, recent controversy surrounding mercury has renewed interest in developing a mercury-free restorative material with physical properties comparable to dental amalgam. Mercury-free metallic restorative materials proposed as substitute for mercury-containing amalgams are gallium-containing materials and pure silver or silver-based alloys. Now, gallium alloys. Whitcomer suggested the use of gallium in dental restoration in 1928. However, attempts to develop satisfactory gallium restorative materials were unsuccessful until Smith and others in 1956 showed that improved palladium gallium and silver gallium materials has physical and mechanical properties that were similar to or even better than those of silver amalgam. Advantages of gallium-based alloys are rapid solidification, good marginal seal by expanding on solidification, heat resistant. The compressive and the tensile strength increases with time comparable with silver amalgam. Creep value are as low as 0.09%. It sets early so polishing can be carried out on the same day. They expand after setting therefore provides better marginal seal. Reaction is the alloy and the liquid are mixed as usual. The structure of the gallium alloy resembles that of amalgam. The reaction between AgSn particles and liquid gallium involves the formation of AgGa phase and a pure tin phase. So basically, AgSn, that is silver tin plus gallium, gives silver gallium plus tin. After mixing, the alloy tends to adhere to the walls of capsule, thus difficult to handle. Moreover, by adding few drops of alcohol, the problem of sticking can be minimized. Now, the properties of gallium. It has the property of wetting many materials, including tooth structure. It sets in a reasonable time and passes the strength, diametrical stability, and corrosion resistance equal to or even greater than that of silver amalgam. Composition. Recent gallium alloys have following composition: alloy, silver 60%, tin 25%, copper 13%, palladium 20%. Liquid, it has gallium 62%, iridium 25%, and tin 25%. Physical properties of high copper, silver amalgam, and gallium alloys. So this is the comparison. So 3% in high copper is 1.04 plus minus 0.06%. In gallium alloys, it is 0.09 plus minus 0.03%. Compressive strength. So in silver alloy, it is 370 megapascals. In gallium alloys, 350 megapascals. Setting contraction or expansion. In silver alloy, it is minus 0.05%, and in gallium, it is plus 0.39%. Now, biological consideration. In early gallium alloys, surface roughness, marginal discoloration, and the fracture were reported. With improvement in composition, these defects were reduced but not eliminated. The gallium alloys could not be used in larger restorations as a considerable setting amount of expansion leads to the fracture of cusps and post-operative sensitivity. The cleaning of instrument tips is also difficult. It is also less popular because it is costlier than amalgam. Now, we have powder coated technology. One approach consists of cold welding silver that is based on a powder technology and transforming it from an extremely plastic mixture to a solid within the prepared tooth at oral temperature. The second approach is to condense a mixture of two intermetallic compounds, that is Ag4SN beta phase and Ag3SN, that is gamma phase, or similar alloy particles that have been silver coated or which have undergone an appropriate treatment in surface activating solution. This technology involves electrochemical powder treatment and the condensation technique, which is similar to that used for direct filling gold foil. During consolidation, the adherence of silver surfaces is enhanced after immersion of the silver-based particles in a solution of 10% fluoroboric acid. The metal segments must be stored in a special acid solution prior to use to remove surface oxides and to enhance cold welding. Thus, this product may be more technique sensitive than dental amalgam and may require more time for proper condensation. Advantages: flexural strength as that of amalgam, smooth surface and hardening was obtained, more resistant to wear because of work hardening. Now, a silver tin alternative to dental amalgams. A novel technology for a mercury-free metallic direct filling material, a substitute to dental amalgams. A dilute acid is used for removing the surface silver oxide layers, thereby promoting the cold welding process. The condensability, namely the ability of a loose powder to undergo consolidation within a short time duration at body temperature and under moderate pressure, has been investigated for a variety of mixtures of silver, tin, and pre-alloyed silver-coated intermetallic powders. The resulting metallic composite materials display transverse rupture strength values higher than those of amalgams and somewhat lower values of compressive strength and nooth hardness. Then, a new dental powder from nanocrystalline melt spun AGSNCU alloy ribbons. A new non-gamma 2 dental powder has been developed from nanocrystalline melt spun silver tin copper alloy ribbons. The amalgam made from this powder exhibits excellent properties for dental filling. The nanocrystalline microstructure was found for the first time in a spun and heat-treated AGSNCU alloy ribbons using X-ray diffraction, scanning electron microscope, and energy dispersive spectroscopy. As spun ribbons exhibited a multi-phase microstructure with preferred existence of Ag4SN phase, formed during the rapid solidification due to supersaturating of copper atoms and homogeneous nanostructure with subgrain size of about 40 to 50 nanometers, which seems to be developed during rapid solidification process and can be caused by eutectic reaction of the Ag3SN, Ag4SN, and Cu3SN system. In heat-treated ribbons, the clustering of copper atoms was always favored and stable in an aging temperature and the time interval determined by copper content. The heat treatment led to essential changes of the subgrain morphology, resulting in the appearance of large angle boundaries with fine Cu3SN precipitates and forming typical recrystallization twins. Such a microstructure variation in melt spun ribbons could eventually yield enhanced technological, clinical, and physical properties of the dental products controlled by area specification number 1 and reported before. Thus, using the rapid solidification technique, a new non-gamma 2 dental material of high quality nanocrystalline ribbon powder can be produced. So, that was the recent advances in amalgam. Now we're going to study about the recent advances in glass ionomer cements. Glass ionomer is the generic name of the group of materials that use silicate powder, glass powder and an aqueous solution of polyacrylic acid. Severe pulp irritation caused by silicate and zinc phosphate cement led to the replacement of phosphoric acid by polyacrylic acid, resulting in zinc polycarboxylate first and then GIC later. Though glass ionomer was originally aimed to be restorative material, soon it was modified as a luting cement also. The early cement was slow setting and highly technique sensitive, but since its introduction, it has undergone many changes. Now, the classification, according to Wilson and McLean in 1988, type 1, luting cement, type 2, restorative cement. In this, restorative aesthetics and restorative reinforced. Then, according to the application, type 1 luting cement, type 2 restorative cements, type 3 lining or base cement, type 4 fissure sealant, 5 orthodontic cement, and 6 cold buildup. According to the characteristics specified by manufacturer, type 1 luting cement, type 2 restorative material. Luting example Fuji 1 key tag, restorative example key tag fill, Fuji 2, Fuji 9, etc. Then we have type 3, bases and liners. Weak with less acidic, GC lining cement, shofu liner. These are the examples of bases and liners in type 3. And we have bases and liners, stronger but more acidic, that is ketag bond, shofu base. And bases and liners, bases and liners, strong even in thin layer. So we have light cure, that is Vitra bond. Then we have type 4, admixtures, that is ketag silver and miracle mix. We have newer classification, traditional glass ionomer, type 1 luting cement, type 2 restorative cements, and type 3 liners and bases. And we have metal modified glass ionomer. In this, we have miracle mix and so much cement. Light pure glass ionomer, we have in this, hema is added to the liquid. And we have hybrid glass ionomer, resin modified glass ionomer, in this composite resin in which fillers substituted with glass ionomer particles of pre-cured glass bended into the composites. Then, according to McLean in 1994, glass ionomer cements, that is traditional, then resin modified glass ionomer cements, and polyacid modified composite resins. Composition of traditional glass ionomer: silica 35 to 50%, alumina 20 to 30%, aluminum fluoride 1.5 to 2.5%, calcium fluoride 15 to 20%. Sodium fluoride 3 to 6%, aluminum phosphate 4 to 12%. Then we have lanthanum, strontium, barium traces for radiopacity. We have in liquid, we have polyacrylic acid 45%, then we have itaconic malic acid, tricarbolic acid, tartaric acid, these are 5%, and then we have water, that is 50%. Malic acid, it decreases viscosity, and tartaric acid, it increases working time and decreases setting time. Water is present in 50%. Then variations in basic glass compositions. Calcium may be replaced wholly by strontium, partly by barium, and both being alkaline earth metals, or lanthanum, a rare earth metal that gives radio opacity. Glasses may be modified by incorporating aluminum fibers, amalgam alloys, and materials. These modifications were made to improve the flexural strength. Then modifications in powder. The modifications were to improve upon mixing existing property in the manipulation and the area of clinical use. Some of the modifications are direct polyacrylic acid, that is anhydrous GIC. Then we have silver tin alloy, miracle mix. Then we have silver palladium titanium, that is so much cement. Then we have bis GMA, tech DM, and HEMA, light or dull GIC. Then we have MVP, CPP, ACP, zirconia, etc. Then modification in liquid, only water and tartaric acid, that is anhydrous cement. Then we have HEMA in liquid, that is in light cure components. And we have polyvinyl phosphoric acid. In 1992, polyvinyl phosphoric acid was found to form cements with wide range of metal oxides in aqueous forms. It has a structure similar to polyacrylic acid but contains tangent phosphoric acid groups in place of the carboxylic acid groups of zinc polycarboxylate and glass polyalkanoate cements. It is stronger acid than polyacrylic acid with a greatly increased reactivity towards metal oxides. The physical and the mechanical properties of a number of metal oxides PVPS cements were studied and compared with those of zinc polycarboxylate cements. The faster acting of the metal oxide PVPS cement seems to produce cement that is less susceptible to only hydrolysis. Then diamond curve. Diamond curve is a GIC that has been modified by addition of small percentage of polyvinyl phosphoric acid, phosphorus analog to PAA. PVP has a stronger acid than polyacrylic acid and hence more reactive, chemically more hydrolytically stable. Then we have anhydrous cement. Anhydrous means that the acid has been freeze dried and included in the powder. The polyacrylic acid can be vacuum dried and incorporated with the glass powder. The liquid then used being either water or a dilute aqueous solution of tartaric acid. Its advantages are low viscosity in early mixing stages, rapid set at minimum temperature, easy manipulation, and excellent shelf life. Metal modified glass ionomer cement. Metal modified cements are of two types. Silver alloy admix, amalgam alloys are incorporated into the glass powder. Then we have somat ionomer cement. Precious metals like silver, gold, titanium, palladium, etc. incorporated in glass powder. Silver is commonly used. Glass is generally brittle, and addition of silver was expected to improve the toughness of the cement as silver acts as stress absorber and also improves the abrasive resistance of the cement. In glass cements, this was introduced by McLean and Gasser in 1985. Glass and the metal powders were sintered at high temperature. This was attempted to improve the wear resistance, flexural strength, and at the same time maintains the aesthetics. So, mud cement. The main disadvantages of the conventional glass ionomers are brittleness, poor surface polish, porosity, and surface wear. Improvement in these areas are essential if the clinical use of glass ionomer cements is extended to high stress bearing areas. Cement was introduced in 1984 under the trade name Kitac Silver. The incorporation of the dispersed phase such as corundum, that is aluminum oxide, into the glass can double the flexural strength of the glass ionomer cement. However, little improvement in the wear resistance was obtained. The incorporation of alumina fibers also increased the flexural strength of the cement but resulted in decreased abrasion resistance. Instead, and Wilson investigated the effect of incorporating metal fibers or powders into the glass ionomer powder. Flexural strength were increased, but abrasion resistance was poor because of the lack of strong bonding between the metal filler and the polyacrylate matrix. The problem of containing strong bonding of metal fillers to the glass ionomer powder was solved by sintering the metal powder into the glass powder. Strong bonding of the metal glass composite resulted in the formation of a cement in which, unlike simple mixtures of metal and glass powder, the metal became the part of the glass powder and the strength of the bond was comparable to that of fusing porcelain to gold. Currently, two types of silver cement ionomers are available, one for hand mixing, that is Shillon Silver ESP, and other for the auto mixing in capsule, that is Kitac Silver. This is also ESP brand. In the properties, Kitac silver has been better resistant to abrasion than regular glass ionomer. Occlusal wear resistance was also close to that of amalgam alloy and microfill composite resin. Improved wear resistance could be caused by a lubricating effect of the silver. Flexural strength of the cement ionomers is better than most commercial glass ionomer cements. Fracture toughness is better than the conventional glass ionomer cements. Clinical uses as a restorative material for class 3 and class 5 lesions, core buildup, linings, fissure fillings, restoration of primary tooth, restoration of class 2 lesions. Then, now coming on to the miracle mix, that is silver alloy powder and glass ionomer cement. Adding silver alloy powder to a type 2 restorative glass cement powder and mixing this powder admixture with polyacrylic acid liquid was intended to make its first metal reinforced glass ionomer cement radio opaque and harder. Addition to this spherical silver alloy powder to the pure hydrous restorative type 2 glass ionomer cement is termed as miracle mix. Properties: adding silver alloy powder to the glass ionomer improves compressive strength, tensile strength, creep resistance, less micro leakage, and increased dynamic flexural strength. Resin modified glass ionomers, they were introduced to overcome the problems associated with the conventional glass ionomers and at the same time preserving the clinical advantages of conventional materials. These combined the technologies of resin composites and conventional glass ionomers. In general, the resin modified glass ionomer materials are the hybrid of a glass ionomer and resin composites. In 1988, Otto Nishi et al. Introduced the first light curable glass ionomer cement, and this was formed as a combination of conventional glass ionomer cement with light cured resin composite. The advantages included immediate stabilization of the water balance following the light initiation, as well as enhanced translucency and the ultimate restoration. The main disadvantage appears to be the need for incremental build-up for the restoration deeper than 3 to 4 millimeters because the light penetration is limited to that depth. However, there is a safety factor in as much as acid-base reaction will continue, even in the absence of light activation. In addition, the presence of redox reaction in the resin component ensures complete setting of the entire restoration under all circumstances. The classification of the resin reinforced glass ionomers depends on the curing mechanism. First is dual cure, visible light cure, free radical polymerization, and glass ionomer setting mechanism. So acid-base reaction is there. For example, Restore. In this, so dual cure, what happens in dual cure is we have visible light cure, free radical polymerization, as well as we have glass ionomer setting mechanism. That is acid-base reaction. An example for dual cure is Restore. Then we have tricure. And this visible light free radical methacrylate polymerization. Then we have chemical cure of free radical methacrylate polymerization of composite resin, and then we have conventional acid-base reaction of GIC. Okay, so example is Vitrimer, Fuji2LC, etc. In photocure, visible light cure only. In this polyacid modified composite resins, variglass, compoglass, diarite, high-tech are the examples. In autocure, chemical cure of the radical methacrylate polymerization, only autocure happens. This example is Prostodont. Once activated by intense visible light, they set rapidly. The reaction is dual setting. The normal glass ionomer cement acid-base reaction. Free radical or photochemical polymerization process similar to that used in composite resin. Now, acid-base reaction, calcium aluminosilicate plus polyacrylic acid is equals to calcium plus an aluminum polysol hydrogel. So when calcium aluminosilicate and polyacrylic acid mix, it forms a hydrogel of calcium and aluminum polysalt. So this is in GIC, this happens, this is acid-base reaction. And polymerization reaction in this HEMA plus photochemical initiator or activator, this polyhema matrix. Now, advantages of resin modified glass ionomer cements over conventional glass ionomer cements. Sufficiently long working time control in command to a snap set by photocuring. Improved setting characteristics, protects the acid-base reaction from the problems of water balance. Rapid development of Oli strength can be finished and polished immediately after set. Repairs can be easily carried out as the bond between old and new material is very strong. Exhibits increased adhesion to composite when used as a base. Ideal under the composite as it can be etched immediately. Fluoride release is greater than conventional glass ionomer cements and compomers, and diametrical strength is high, that is 20 megapascals. Then we have resin modified glass ionomer cement. A comparison of water absorption characteristics. The purpose of this study was to quantify and compare the amount of water absorbed by 6 commercially available resin modified glass ionomer cements and to investigate the possible influence of climate and resin content on the water absorption. Materials evaluated included Berry glass used as a restoration base and liner Fuji 2LC, Fuji liner Vitribond, Vitrimer, and Fortag bond. Z100 a composite resin was used as a control. Berry glass, when used as a base or restorative, had a least water absorption both after both 1 week and 1 month storage in water. The degree of water absorption was product dependent and appeared to be influenced by resin content. Disadvantages: biocompatibility is controversial. Setting shrinkage is higher, micro leakage is more, marginal adaptation is poor. Lower wear resistance compared to composite, poor fracture toughness, color that cannot compare to composite in its ability to match the natural tooth coloration. Uses: used for luting stainless steel crowns, space maintainers, bands, and pedo cases. Used as a liner and base, pit and fissure sealants. Example: Fuji 2LC, Fortac Fill ESP, Vitribond 3M, and Vitrimer 3M. Core build-up material, repair material for damaged amalgam cores or cusp, and retrograde filling material. These are the uses. Then we have Fuji 2LC improved. This is a light cure resin reinforced glass ionomer restorative material introduced by GC Corporation, Tokyo, Japan. Fuji 2LC improved has all the advantages of traditional glass ionomer along with important advances, including triple curing, immediate finishing, outstanding aesthetics, simplified technique, and significant time savings. Fuji 2LC improved has smaller particle size for greatly improved polishability and a conditioner which provides enhanced bond strength. So, this was Fuji 2LC improved. Now, coming on to Fujibond LC. This is a resin reinforced light cure glass ionomer for bonding composites. Fujibond LC is a bonding agent that protects and seals against micro leakage and eliminates sensitivity. This requires simple and very easy application. The coefficient of thermal expansion of this material is closer to that of tooth. It provides all the benefits of a true glass ionomer and the composite restoration. So, this is so we are studying the modifications of GIC. In this we have studied resin modified, Miracle Mix, Sawmill, Fujibond, LC modifications in powder, modifications in liquid, Fujibond improved. We have many more to go in the next class. Thank you. We'll continue in the next class.